Okay, in this video we're going to talk about the quantization of photons and packeting energy, really, in terms of photons. And we're going to lead us up to the photoelectric effect and the photoelectric equation of Einstein's. So initially what we're going to look at is we're going to look at the equation E is equal to hf. Now this equation is quite profound because effectively it means that the energy a photon has is directly proportional to the frequency. So if you're thinking about what the EM spectrum, then obviously the highest frequency on the EM spectrum, gamma rays, have the highest energy because they have the higher frequency. So that's a nice relationship to draw there. Now obviously we can change frequency because frequency from V is equal to F lambda, F is equal to V over lambda, and since we're talking about light, we can change this equation to be E is equal to hc over lambda. When we input this equation, we're replacing F with it. So effectively there we're able to put together two equations to show how energy is related based on its wavelength, of course, as well as its frequency. Now, the concept of quantization of photons is more important when we study the photoelectric effect. Now, the photoelectric effect is effectively where photons interact with electrons in a material and allow them to be released. So in comes our photon, and effectively it interacts on a one-to-one basis with electrons in the surface of this material. And if it gives them enough energy, then the electrons can be released. And effectively we call these photoelectrons. So photoelectrons are released, and it gives them some kinetic energy. So the equation that relates all of these together is Einstein's photoelectric effect equation, which we start out with hf is equal to phi plus ke max. So let's talk about each of these terms individually. Well, hf is the energy the photon comes in with. So that's the amount of energy the photon has as it comes in. Now when it interacts with this electron, it has to release it and then have some energy left over to give it kinetic energy to make it fly away. So the energy required to release an electron from the surface of the metal, or material in this case, is called the work function. And it's the amount of energy that is required to release an electron from the surface of that material. So, energy required to release from the surface. Whatever's left over, so this is a fixed amount for this material, so whatever's left over is the kinetic energy that is going to go into allowing this photoelectron to fly off in that direction. So this is left over. And it's a maximum Ke because if the electron is on the surface, then it requires that much energy. That is the minimum amount of energy required. This, therefore, would be the maximum that could possibly be left over from the initial energy of the photon that could be used as kinetic energy. And it's important to note that kinetic energy would utilise the half mv squared equation in this circumstance here. Now it is important to realise that this is a one-to-one relationship, and the concept of intensity is very important here, because intensity, when we think of intensity, what is increasing? So if I increase the intensity of this, well, intensity is a measure of power over an area. Obviously this would be our area. So if I'm increasing the intensity, I'd have to increase the power. Power is an amount of energy transferred per unit time. So there's two ways you could consider that we might increase the intensity here. I either increase the energy of the photons, or I increase the number of photons. Intensity is directly linked, in this case, to the number of photons that is incident. By incident, I mean allowed to hit that surface or that area. So the point is here that the intensity is dependent on the number of photons, not the frequency. Intensity is not related to the energy and hence the frequency of those photons. So that's kind of a brief rundown of the photoelectric effect. It's all basically energy of photon, energy given to electron, enough energy to release it, minimal value. It's also called known the work function. Ke max is the maximum kinetic energy. Another term that goes along with a lot of this is the threshold frequency. Now it's related to the work function, because the work function is a minimum amount of energy. Therefore, there must be a minimum amount of frequency to allow that electron to be released. So the work function would be equal to Planck's constant, which we'll talk more about in the lesson. We'll actually do a practical to determine it, and frequency, which is the threshold frequency. It is the minimum frequency of a photon that allows for an electron to be released from the surface of the material. So the work function is the minimum energy required. Therefore, the threshold frequency is the minimum frequency required to release it from the surface of that material. So it's all about minimums here. The work function is always to do with that minimum electrons on the surface. Obviously, there's electrons deeper as well. Deeper electrons will require more energy, so therefore the value of this is no longer the work function, it's another form of energy, and so you're not going to get Ke max. But it is still going to add up to HF in this circumstance. Okay, so have a good think about that. We'll do some demonstrations around the photoelectric effect when you come in next time, and we'll see how you do.